Alright, let's talk about Chapter 2 now, plate tectonics. So plate tectonics started as early as 1620 when Sir Francis Bacon first noted that coastlines along South America and Africa seemed to fit together like a jigsaw puzzle. Now, he just suggested that they seemed to fit together, but he didn't provide any evidence or didn't provide a hypothesis as to why that was the case. He just made an observation. So essentially, he started off the scientific method for plate tectonics, but didn't go any further than that. Much later, in 1915, we have Alfred Wegener, who revisited the topic of plate tectonics and continental drift, and he went so far as to propose a theory for continental drift. But he failed to provide a mechanism for how continental drift occurred. He is credited with coming up with the term Pangaea for the large landmass that was formed by all the continents coming together. And he also termed the large ocean Panthalassa, which we'll talk about in a little bit. But at that time, in the early 1900s, he was met with a lot of criticism for his theory, as well as a lot of people who just didn't believe him, because in his theory, he stated that the continents drifted around the Earth by plowing through the ocean basins, and that mountains were formed by drag. So that didn't seem too plausible. He also said that the driving mechanism for continental drift was the gravitational attraction and the tidal forces. So that didn't make much sense at the time to the other scientists. And because he couldn't provide a plausible mechanism for continental drift, a lot of them thought his theory was too far-fetched, that it was contrary to the law of physics at the time, which I can kind of agree. I mean, you can't really form mountains from drag. That would be interesting if that were the case. And at the time, they lacked technology to prove continental drift. So nowadays, we know that continental drift is a proven theory. We have GPS that can show the plates moving at a very, very slow rate, but they still move. But at that time when he proposed this theory, they didn't have that technology. So he was just basing it off of other observations that he had noticed. So if we look at this graphic here, you can see about 250 million years ago, that's when we had Pangaea together as one landmass, and you had the really large ocean known as Panthalassa. And you can see this diagram goes through the years. So in about 200 million years ago, you start to see Pangaea breaking apart into two separate continents. You have the Laurasia and Gondwana, and at this point you have Pangaea split into two larger continents, and this is the beginnings of continental drift. And then you see in the Jurassic period, you have that was at 150 million years ago, you start to see the continents that we know today starting to split apart. And you'll see over time it continues to split apart until you get to now, where in the bottom right hand corner, where you see that 100,000 years ago we had an ice age, but more or less the continents are in a very similar spot to where they are right now. So what are the 5 pieces of evidence that Alfred Wegener suggested in his theory of continental drift? So he first stated that continental shape, Then we're going to talk about similar geology, then fossil evidence, volcano and earthquakes, and paleomagnetism. So those are the 5 pieces of evidence that he used to build his theory. So let's talk about each one now. So for continental shape, it's just as Sir Francis Bacon suggested. When you look at South America and Africa, the coastlines seem to fit together very well. So you can see the eastern coastline of South America matches up very well with the western coastline of Africa. And you can see those red spots are just places where the landmass would have overlapped. But when the continent broke apart, some of that probably tore up and fell into the ocean, or just broke apart. And over time, erosion along the coastlines would have changed the coastlines just a bit. But if we look at this next slide, you can see that Panthalassa was the largest ocean. You have the Tethys Sea, which is sort of near where Africa and the Eurasian continent would have been on Pangaea. And when you put all of the continents together where they should have been at, you can see that they line up more or less perfectly, with little gaps areas between, say, like North America and South America. You have this very large body of water between them, but you can also see the Indian continent attached to the Antarctic, and you've got the Australian continent off to the side over there, but they all more or less fit together like a puzzle piece. So the next one we'll talk about is similar geology. When you look at rocks on different continents, the rocks nearest to coastal areas, for instance, in North America and in Europe, you can see that there's this very large mountain range on the east coast known as the Appalachian Mountains. And in Europe, in the Scandinavian Peninsula, you can see there the Caledonian Mountains. Now, when we put these continents back together, as they were in Pangaea, you can see this mountain range is just one long mountain range that extended all the way from where Florida should be, all the way up into Europe. And when these continents broke apart, the mountains split in half, went their separate ways, and when you test the chemical minerals within the rocks, both in the Appalachian Mountains and the Caledonia Mountains, they are similar in composition. So that's how we know that the continents were together at one point. Also, when you look at Antarctica and the continents that surrounded Antarctica, you can see that there are similar glacial deposits on all of the continents surrounding Antarctica. So Australia, India, Africa, and South America all have very similar glacial deposits. What I mean by glacial deposits is anything that the glacier picked up. So it could be plant material that it froze or rock material, and it would have distributed it as it flowed along the land. And when it receded, when the weather got too hot and it melted and receded, all of that rock material would have been left behind. And so all of that material that was on Antarctica that was pushed over onto the other continents from the glacier and left behind all have very similar chemical compositions in their minerals. Next, we should look at fossil evidence. So when we look at fossils on different continents, we tend to see very similar fossils. So the image on the top there shows a Mesosaurus fossil found both in Africa and South America. This is a crocodile-like or alligator-like animal that used to live back in the time of Pangaea, so about 250 million years ago. And you can see the range in which this organism lived. It was a pretty large range. And this organism also doesn't look like he can swim very far, especially not across an entire ocean basin. And so it's been theorized that at one point in time, these two continents were connected. That way, it would allow for this organism to freely roam around its entire range unimpeded. And if we look at the two images on the bottom there, the koala and the marsupial, or not marsupial, the possum, sorry, on the left-hand side, and you'll see that these organisms have similar ancestries. So these organisms at one point in time probably had a wide range between North America and Australia, and when the continents started to break apart because of continental drift, these two organisms became isolated from each other. So whatever the common ancestor was became separated, and each group, so the possum on North America, would have had a separate amount of resources, different living conditions, different environment that it would have had to have dealt with compared to the koala on Australia, who also had a different type of food resources, predators, and environment that it had to deal with. And so over time, these two organisms evolved very differently. So you can see the possum, they are both marsupials, and you can see that they look very different. But at one point in time, they did have a common ancestor, so they were related to each other. But because they became isolated from each other, they could no longer interbreed with each other and have evolved to the point where they can no longer breed with each other if you brought them back together. So they are genetically distinct. So if we look at this next figure here, you can just get a sense for the ranges for different organisms and plants, or the one plant, across the Pangaean continent, or half of the Pangaean continent. So you can see this fossil of this land reptile and the Mesosaurus. So both of those reptiles extended across South America and Africa. And then you can also see this. You have another land reptile whose range extended from Africa into India and even into Antarctica. Then you have this plant species who have fossils on all of these continents: South America, Africa, India, Antarctica, and Australia. So in that sense, this type of plant probably didn't travel very far and probably needed organisms to help it propagate, just like plants nowadays. But if these continents were separated and not together, it would have been much harder for this plant to have been found on all of these different continents here. So evidence would suggest that since we find fossils on all of these continents, that it was probably a good bet that all of these continents were connected at one point in time. So next piece of evidence, let's talk about earthquakes and volcanoes. And here are two images of the plates that we know of and the boundaries, as well as where we see active earthquakes along subduction zones. And so in the left-hand figure there, each dot represents a different earthquake that has happened at some point in time that we have recorded. So you can see here along the edge of the Pacific plate, you can see tons of volcanic activity, tons of earthquake activity. So when these plates interact with each other, they cause earthquakes, and when they are pushing against each other, they cause these earthquakes and volcanoes to happen, which we will talk about a little bit later in this lecture. But essentially, if we didn't have the plates moving, we wouldn't have volcanoes or earthquakes near these boundary zones. So on this next figure here, we all know about the ring of fire around the Pacific plate. And you can just see different areas where we have active volcanoes. And you can see here in Hawaii, we have some active volcanoes, but wherever, unless they are hotspots, which Hawaii would be a hotspot and you would have a volcano in the middle of nowhere. But generally speaking, majority of volcanoes are located along plate boundaries. And so this was another piece of evidence that Alfred Wegener suggested for his theory of continental drift. Here we can see plate movement. This is a more recent measurement, since back when Alfred Wegener proposed this theory, he didn't have a way of measuring the movement. But today we can see what the movement is via satellites. And you can see that the Pacific plate is the fastest moving plate out of all of them. And you see that it's not moving at the same rate across the entire plate. There are places where they are moving slower or it's moving faster. So in the Pacific, you can see down at the bottom near the Nazca plate and the Antarctic plate, the Pacific plate is moving at a rate of about 18 centimeters, or I'm sorry, 18 millimeters per year. And that's versus, let's look at the Atlantic now. The Atlantic is spreading at a much slower rate. Let's just say average about 2.5 to 3 millimeters per year. So it's essentially the same rate at which your fingernails grow, And so these particular plates overall, when you compare the size, don't move very fast at all, but they do move and they do interact with each other. So the red lines are the boundaries, and the areas that have the triangles that look like teeth, those are subduction zones, and that's where the oceanic crust is being destroyed and sunk back into the mantle. And then the areas that are just solid red lines with arrows pointing away from them, that's where you have a divergence. And that's where new crust is being formed at. So in the Atlantic, the line that runs right down the middle, that is the mid-ocean ridge in the Atlantic Ocean. And so that is creating new crust on a daily basis. All right, so now let's look at the last piece of evidence, paleomagnetism. Paleomagnetism talks about the magnetic material in rocks. And when a rock is formed, so at the mid-ocean ridge where you're creating new crust, you get iron minerals in it from the mantle. And that iron will then orient itself to whichever way is north. So iron is magnetic, right? And you'll have a portion of it that points north, and you'll have another part of it that points south. And so much like this high school experiment on the left-hand side, if you were to put a bunch of iron shavings on the table and then put a magnet down, you'll see these arcs that form in the iron shavings that connects the North Pole to the South Pole. Right? So some of it's being attracted to the North Pole, some of it's being attracted to the South Pole. So this is what happens to iron in rocks. It orients itself to wherever magnetic north is at that time. So if we look at this thing known as polar reversals, we've all heard about scientists saying, yeah, the poles are going to reverse at some point in time and it's overdue. Well, that's what they're talking about in this sense, that over the lifespan of the Earth, the North Pole has not always been in the north. Sometimes it's been in the south, but it's the north. right, at that point in time. So these rocks, whenever they were created and formed, have created what you would call a record of how many times these poles have reversed, and whether the pole was in the north that we know as the north, or if the North Pole was in the south as what we know as the South Pole. All right, so this pattern, scientists have not been able to figure out a predictable pattern to when these pole reversals will happen. But what we do know is that in the past 76 million years, there have been 176 reversals. So that's how many times the poles have reversed. And our present orientation, where North Pole is in the north, has lasted for about 60,000 years. So that's why they say, well, maybe it might be time overdue for a pole reversal. But they're not completely sure about that. Because if we look at this next slide here, you can see from the mid-ocean ridge, you can see as you get away from the mid-ocean ridge, you'll see different pole reversals. So right now, let's just say a positive anomaly correlates to the North Pole being in the north that we know. And so you can see that in this case, it's still being in the north, right? The North Pole is still in the north. But if you were to look at the next strip is negative. That would mean it's a negative anomaly, which would mean that the North Pole was in the south. So when you, and this is not to scale now, but if you were to just infer that, okay, if the positive coming off of the mid-ocean ridge is what we are currently experiencing now, and that is about 60,000 years, then you can see that the pole reversal that happened right before this one had a very short lifespan, right, in comparison to what we're experiencing now. And then if we look at the positive after that, that was also very short-lived. But if we look at that second negative that's really large, well, you can see that one probably lasted maybe 80,000 years, right, where the North Pole was in the South Pole. So you can see that there's really no predictability. There's no real pattern to how long these pole reversals last or to what frequency they will occur. So it's something that we know happens. This is also a way for us to understand continental drift, because as you get away from the mid-ocean ridge, you move the plate. You're basically you're creating new material and you're pushing the plate away from the mid-ocean ridge. And you're pushing it towards a subduction zone. So you're moving material from one place to the other. So if you happen to have a continent plate next to it, you're pushing that continental plate away from the mid-ocean ridge. So this is another piece of evidence for continental drift. All right. So with that being said, let's talk about seafloor spreading, because to have continental drift, you have to have basically new crust being made. You have to have some sort of mechanism for creating new material, because if you're destroying material, then you have to create new material. And so where Alfred Wegener failed to provide a plausible mechanism for this, we now know today that the mechanism for seafloor spreading and continental drift is known as slab pull. Okay, so that slab or the crust part would be known as a slab. And so it's basically a push and pull of the spreading center and the subduction zone that is causing continental drift. So at the mid-ocean ridge, which is also known as the spreading center, you have new material, new crust being made. And so you have magma coming up and it's turning into crust. And when it pushes the old material off to the side to create space for the new material, it pushes that old material down into a subduction zone underneath another plate. And in this picture right here, you're pushing oceanic crust underneath a continental plate. And so when you're pushing that under, you're destroying it because you're sending it back down into the mantle. So it's a push from the spreading center, and it's a pulling of the oceanic plate underneath the continent plate. So it's that push and pull action that actually causes continental drift. At one point in time, they thought maybe it might be mantle convection, where you see the material in the mantle convecting and moving about, but that was deemed implausible because that wouldn't provide enough movement for the plate or enough friction to move the plates as they are today. All right, so let's look at this schematic right here. This is just a general schematic of an ocean basin and the type of plate boundaries that you would have. So in the middle there, you have your spreading center or your divergence zone, and that's where you're creating new crust material. You are creating oceanic crust at that point. Okay, you would not be creating continental crust. So the material at the mid-ocean ridge is solely basaltic material. Right. If we look to the right-hand side of the mid-ocean ridge, you see the plate is being subducted underneath a continental plate, right? And as that oceanic plate is melting in the mantle, it's that melted material is now less dense and lighter, so it seeps up back underneath the continent, and it creates volcanic mountains. These volcanic mountains are known as a continental volcanic arc. So you have the mid-ocean ridge, you have the abyssal plains, and then you would have a subduction zone, which is also a trench, and then you have your continent, which your continental plate will never subduct underneath the oceanic plate. And we'll get to that in a little bit, but that's due to the density of the materials. But so you have your trench, and then you have your continental volcanic arc, okay, which is just your volcanoes on land. So a good example of volcanoes on land would be Mount St. Helens, all right? And we'll get into the characteristics of these volcanoes in a little bit, all right? But if we go from the mid-ocean ridge and we go to the left, we still have a little bit of abyssal plain, and then we have another trench, a subduction zone, but this time it interacts with the oceanic plate, not a continental plate. So when that oceanic plate subducts under the other oceanic plate, you create what's known as an island volcanic arc. So it's a little bit different. You're creating islands now instead of creating mountains. These islands are basaltic material, so they are not land material, even though they are land above the ocean. But the material that's coming up is basaltic in nature. Okay, so we'll cover this in more detail in the next slides. So here, just the plate boundaries again, all right? So you'll see the little teeth, triangles that create teeth, those are where you have your subduction zones, and that's where plate material is being subducted and is being destroyed in the mantle. Now, the places where you see just a solid red line, those are your mid-ocean ridges or your divergent zone, and that's where material is coming up from the mantle and being created. So you can see that they spread at different rates. So at some point in time, the Atlantic Ocean will continue to spread apart and become quite large compared to the Pacific Plate, which may not be as large as it is today at some point in time. Okay, so let's look at the three different types of plate boundaries that exist on Earth. We have the first one being divergence, the second one being convergent, and the third one being transform. So let's cover each one individually now. So divergent plate boundaries are your mid-ocean ridges or your spreading centers, and this is where material is being created at. So Whether this material is being created on land or in the ocean will determine what sort of material creates what. So if you have a mid-ocean ridge, like the mid-Atlantic one right here, then you'll be creating basaltic material. Now if this were on land, if this ridge was on land, you would be creating granite material. But that doesn't happen as often. Okay? So on the diagram on the right there, you can see that there is a rise in mantle material, and it heats up the crust to the point where it starts breaking it apart. And then once it gets to the point where it can break through, it's heat up the crust enough so that it can basically crack it and come through. Then it creates a ridge, it creates new material, and that new material is then pushed off to the side to make room for more material. Alright, so on this next slide here, you'll see a rift valley. Now, rift valley is the beginning stages of a divergent zone. Alright, so in Africa here, unfortunately we don't have any examples in Hawaii that I can show you, but in Africa, then you have the Red Sea between the Arabian Peninsula and the African continent. That Red Sea was created by a rift valley. So at some point in time, the Arabian Peninsula and the African continent were together. They were one solid piece of land. And then at some point in time, you have mantle material coming up underneath this spot right here, heating up the land and causing it to crack. And then eventually it gets to a point where it's so brittle that it starts to break apart. And that new material that comes up starts to create new crust. And so eventually it'll spread far apart enough that it'll start to let water in, ocean water. And so then you start creating a sea. And so here the Red Sea, that's how the Red Sea was created. And if you look at Somalia, there is also a rift zone being created in Somalia, which we will zoom into right now. So if you look at this next slide here, this is an aerial photo of the Rift Valley in Somalia. And you can see here the land is starting to crack. It's starting to spread apart, but it hasn't completely cracked to the point where ocean water has started to come in yet. But eventually over time it will, and then you will get another sea. And eventually, if the Rift Valley extends far enough, Somalia may eventually not be connected to Africa at some point, and it might just become its own continent. Alright, so here is the progression of a rift valley. You can see the warping of the crust in the first image there, and you can see that the mantle material comes up and it's warping it, it's cracking it, it's heating it up to the point where it becomes more pliable and new material can come up and start spreading. And then it will spread to the point where it starts to let ocean water in, and then it becomes a linear sea. And then it gets to a point where it's pushed the continents so far apart that now you have an ocean in between them. And so that's the point at which the Atlantic Ocean is at right now. For the mid-ocean ridge, we have a very interesting case. At the northern part of the ridge, we have Iceland. Okay, Iceland is an island on top of the mid-ocean ridge, but there is continental rifting occurring on Iceland, and that's because the mid-ocean ridge is spreading apart. So in the top image on the right hand side there, you can see rifting occurring on Iceland, and let's compare that to the rifting that's occurring on Somalia. So do you think that the continental rifting occurring on Iceland will eventually split the island apart? Will it become two separate pieces of land? If you guys had said yes, then unfortunately, I'm sorry, you're wrong. But what's actually happening at Iceland is there is also a hotspot under Iceland. So not only do you have the mid-ocean ridge that is spreading material apart, but you have this hotspot that's also bringing material to the surface. So you are not only increasing the amount of crust that's or land that's being made, but you have the mid-ocean ridge spreading it apart. So eventually you'll get to a point where you have one giant land mass known as Iceland. Now let's talk about convergent zones. Convergent zones have 3 different types depending on what crust type is interacting with another crust type. So the first one we'll talk about is an oceanic crust interacting with a continental crust. The next one we'll talk about is an oceanic crust interacting with another oceanic crust. And the third one that we'll talk about is a continental crust interacting with another continental crust. So the first one is an oceanic crust interacting with a continental crust. And here, a good example is the west coast of the United States, along California, Oregon, and Seattle, or Washington, I should say. And you have the Pacific Plate interacting with the North American Plate, and the North American Plate is a continental crust. It is less dense than the oceanic Pacific Plate, and so the plate that will always be subducted is the oceanic plate, the one that is more dense. You'll never see the continental plate being subducted in this situation. And in this situation, you create continental volcanic arcs, so your volcanic mountain ranges. So the Cascade Mountains in the North American continent is a prime example of a continental volcanic arc. And Mount St. Helens is just one volcano along this arc here. All along the mountain range are volcanoes. And these types of volcanoes are what's known as andesitic volcanoes. They are made from granite material, and since granite is not a very porous material, it creates very explosive volcanoes. And so when Mount St. Helens exploded in the early 80s, it had a very violent eruption, and half of the mountain actually collapsed upon itself after the eruption. So you can see this diagram on the next slide here. You can see the oceanic plate subducting under the continental plate. When that oceanic plate melts, all that material that melted rises up underneath the continental crust, pushing that continental material upwards, creating a mountain, and therefore a volcanic mountain, where material will spew out onto the land. It will create new land, new continental crust. So this is the only way that you can create new continental crust. And you generally will have that trench off the coast of the continent. So you'll have the oceanic crust, the trench, and then you'll have your continental coastline, and then you will have your continental volcanic arc. Next, we'll talk about the ocean-to-ocean interaction. And here in this slide, we have 2 oceanic plates meeting together. And in this case, since they are both oceanic plates, you have to take whichever one is the least dense, and that's the one that stays afloat, and the one that is more dense subducts under. Now keep in mind, I did say the average density of the oceanic plate was about 3, but that's just an average density. Each plate has its own specific density, and so when these 2 plates come together, whichever one is the heaviest will subduct. And so in this case, this is an example. You can use this as a Pacific Ocean example. And here you have the 2 plates meeting. The Pacific plate will be subducted, and then that material that's melted rises up and creates volcanic islands. These volcanic islands are made out of basaltic material, and these are known as volcanic island arcs. And so generally these types of interactions will create these types of volcanic islands as well as very deep trenches. So in the Western Pacific, you'll see the Marianas Trench. That was created by an oceanic to oceanic interaction, and that is the deepest trench that we have on Earth. And then lastly, we have the continent to continental interaction. And in this slide here, you'll see that when you have two continents interacting with each other, you generally create mountain ranges. So in this example, we have the Indian continent interacting with the Asian continent. This was the last known interaction of this type. We don't have any other of these interactions currently happening. Granted, this particular interaction is still occurring. The Indian continent was pushed northward from the ocean ridge in the Indian Ocean, and as this Indian continent moved closer and closer to the Asian continent, there was less and less ocean in between the two continents, until it got to a point where there was no ocean left, and all there was the Indian continent hitting the Asian continent. So let's look at this figure on this next slide here. You can see where the subduction zone is in between the Asian continent and the Indian continent, as depicted by the red line with the triangles that kind of look like teeth. You can see it wraps around the Indian continent all the way around down under the Indonesian islands. And here, the Tibet country, that is all just transform faults, but essentially it's a giant mountain range that is continuously being compressed because the Indian continent, or the Indian landmass, is continuously being pushed up into the Asian continent. And so it is continuously pushing material upwards. So if we look at this figure here, you can see when there was still ocean in between the Indian and the Asian plate, you had a very active subduction zone. You had material melting, you had a continental volcanic arc on the Asian continent, and then once there was no more oceanic oceanic crust to subduct, that Indian continent smashed into the Asian continent and shut off the subduction zone. So there was no more subduction in this area. You no longer had any volcanoes. So all of those mountains in the Himalayas used to be volcanic, but are no longer volcanic anymore because no material is being pushed upwards. But you still have the Indian plate pushing into the Asian plate, and so what is left of the Indian landmass is continuously being pushed into the Asian plate, and so all of that material will eventually turn into one large mountain range known as the Himalayas, and so it will continue to grow. It will continue to transfer material into the mountain range. So at some point in time, India will no longer be a country. It will be part of the Himalayan mountains. And then lastly, we have the transform fault plate boundary interaction. And a good example of the transform plate boundary type is the San Andreas Fault in California. This is a land transform fault because it occurs on land, not in the ocean. A good example of an ocean and transform fault would be a mid-ocean ridge. So along the mid-ocean ridges, you have transform faults that split apart the mid-ocean ridge. Well, in a transform fault, you have the plates not pushing or pulling each other. You have them sliding past each other. So you don't get any volcanic activity in this type of plate boundary, but you do get a lot of earthquakes. And so people in California know this very well. But these particular interactions release a lot of energy, and so that's the reason why these types of plate boundary interactions can cause some really, really large earthquakes. And then next, so outside of the plate boundary types, we have these random hotspots, essentially mantle plumes that come up in the middle of a plate, and they create islands. And so Iceland is one type, but the Hawaiian Islands are also another type that are created by hotspots. And so when we look at the orientation of the islands within our island chain, you can see Hawaii is in the middle here. And if you follow that purple line, you can see that the plate is traveling in a northwestern direction. And at a certain point, you see the purple line bend up towards north. And that is that part of the island chain is known as the Emperor Seamounts. And that is still part of the Hawaiian Islands. And so why does that part of the island chain point northward? At some point in time, when before the main islands were formed, the Pacific Plate was moving in a more northerly direction. But when you have plate interactions such as continental and continental interactions, you can get some pretty massive changes occurring around the world and to the other plates. So when the Indian continent smashed into the Asian continent, it caused a whole shift in all of the plate movements around the world, which caused the Pacific Plate, in this example, to start moving in a more westernly direction instead of northerly direction. So you can see that shift in plate movement, and this happened across all of the different plates. And then we see here on this next slide a topography image of the area surrounding the Big Island. And you can see the different volcanoes on the Big Island. There's 5 of them. You have the Kohala Mountain, the Mauna Kea Mountain, the Hualalai, the Mauna Loa, and Kilauea. So those are the 5 different volcanoes that made up the Big Island. Kohala is extinct. It's no longer an active volcano. It has drifted far off of the hotspot that it's no longer being fed by it, so it's no longer active. Mauna Kea is dormant, and while an eruption off of Mauna Kea is not likely, there is a slim chance that it could erupt, but there have been no evidence of any activity occurring in the mountain, unlike Hualalai and Mauna Loa, which are still listed as active volcanoes. So Mauna Loa is an active volcano, as well as Hualalai, although they are not actively erupting at the moment. They have erupted within the last 100 years, so that is the reason why they are still classified as active. Whereas we have Kilauea, which is actively erupting and creating new island material on the Big Island. But we have our newest volcano popping up off the coast of the Big Island, and this one is known as Loihi. This will eventually, at some point in time, create a new island, but for the moment it is just a seamount because it hasn't come up above the water's surface. So here you can see a topography where you have the reddish materials in the water now and on land. The red-orange color indicates a shallower depth, whereas the purple colors indicate a much deeper depth. So you can see at Loihi, it's coming up a little bit. It's probably about an average of 4 to 5,000 feet, 4 to 5,000 feet deep at the moment, the topmost part of Loihi. So it still has some ways to go before it completely surfaces above the ocean floor. So Loihi is a seamount, and generally speaking, seamounts are cone-shaped. You can just think of an ice cream cone turned upside down, and that would be what a seamount typically looks like. They generally originate from a hot spot, so they need to have some magma material contributing to them because they are active volcanoes just underneath the ocean, and they have not surfaced above the ocean surface, so that's the reason why they're known as seamounts. But in contrast, we have these other features on the seafloor known as table mounts, and these table mounts are similar to seamounts, but they have a flat top. So they also are not actively volcanic. They used to be volcanic islands that were above the ocean surface, but over time they eroded by wind and waves and eventually sunk below the ocean surface. So because of that, they are no longer conical in shape, but they have more of a mesa-like shape where the sides come up and then there's this flat top. So if we look at the progression from an active volcano to a table mount, you can see on the right hand side of this image, you have your active volcano. It's above the ocean surface. And then at some point in time, it leaves the hot spot, becomes an extinct volcano. It is eroded by wind and waves until it gets to a point where it becomes an atoll, where you have a coral reef surrounding a sunken island. And then eventually, once it gets really far down the line, that a sunken island will continue to sink below the ocean surface, and then you'll get a table mount with a flat top, and it's no longer active, so it's not a seamount anymore. And then the atolls, so the progression from an island above the ocean to the island becoming extinct and sinking, the coral reefs that surround the island don't just sink with the island. For atolls, the process begins with the island, an active volcanic island, and surrounding that you have a fringing reef. So that reef, that coral reef, is attached to the island, and it grows outward from the island. And then over time, as that island leaves the hot spot, so no longer becomes a volcanically active, it starts to sink below the ocean surface. And as the island sinks, the coral reef doesn't sink along with the island, it stays put. So it continues to grow and essentially forms a footprint of where the original island used to be at. And what happens is you end up with this lagoon-like thing that separates the coral reef from the remaining island that's still above the surface. And then as you get a little bit further along, the island completely sinks under the ocean surface, and what you have left is just a ring of coral where the island used to be at. And so this coral continues to grow, continues to thrive, and this is what's known as an atoll. So in the northwestern Hawaiian Islands, a lot of the islands up there are actually atolls now. The island is still there, it's still under the ocean, but it's no longer visible from the surface of the ocean. You have to dive down in order to get to where the island is at now. Barrier reefs, that's what happens when the island starts sinking. And so a famous barrier reef, this would be stage 2 of the process of creating an atoll. So you go from a fringing reef to a barrier reef and then an atoll. And so the most famous barrier reef that we have on Earth is the Great Barrier Reef in Australia. And if you see here, you can see all the different reefs that were at one point attached to the coastline, but as Australia has moved away, it has created this coastline basically in the middle of the ocean of just coral. So some of these corals are miles away from the coastline, and so you have this nice lagoon area right along the coastline, and then you have to go out some distance and you get the coral reefs. So this is just an image of what the coral reefs could look like in the Great Barrier Reef. But essentially coral reefs are like the rainforest of the ocean. They are very diverse in organisms and plants, and they host and they can support a lot of different organisms, unlike different areas in the ocean that we'll talk about later. So here's just some general information about the Great Barrier Reef. It is the largest in terms of area of a barrier reef, and you can just see some statistics about how many different types of fish. So it supports over 1,600 different types of fish, 133 different types of sharks and rays. It has 600 different types of corals found within this reef, and it has it can support different it has 600 different continental islands. So it could just mean it's a barrier reef, so it could have sediment accumulation and sand accumulation, and so it could have created an island from that accumulation. And then lastly, let's look at what the continental drift has in store for our continents in about 50 million years from now. So you can see the purple shaded areas are where the continents are currently. And then you'll see where they have drifted to. So you can see that the South American continent will continue to drift towards the Pacific plate, and the African plate is being pushed towards the Eurasian continent. And you'll see that India is continuing to be pushed northward towards the Eurasian plate, and so that's just going to make the Himalayan mountains even higher. And you can see the Australian continent is being pushed northward as well too. And so there's just going to be a lot of shifting, a lot of pushing, and you can see that the Atlantic Ocean is expanding while the Pacific Ocean is actually shrinking in this image here. All right, so that was chapter 2. So next week we will talk about chapter 3, which is marine provinces.